x, right?
Yes.
Okay, so is it safe to assume that x is going to be a small number?
Depends on what you mean by small. I would expect it.
Smaller than like 2.
No.
Okay.
Oh, because we're like the sign values are always less than 1, but those sign values are being multiplied, either multiplied or divided with that 8.2. So that's going to change those values into whatever scale they have to be.
Oh, okay. Thank you.
Sure. So if I don't know why my connection is so unstable today. If I do lose you guys, just do keep playing with 5.4 and 5.5. As I said in the beginning, it might be kind of surprising, but we've technically talked through all of 5.4 and 5.5. That's our triangular definition. Like this is 5.5 right here. So we've talked through all that. So you guys can work on that and play with it. We kind of have talked about chapter 5 almost as one whole, as opposed to trying to force it into an artificial separation. So do play with that if I lose you guys for good. And I'll try to figure out why my thing's so unstable. It's not that bad outside, is it? The weather?
Everyone seems to be having internet troubles today. Like my class earlier today was having similar issues.
I know it snowed a bit, but it is not that bad outside last time I checked.
Yeah. I don't know. Anyway, do be careful when you're solving for a variable in the denominator. It does take an extra step or two.
Okay, I did that right.
So what did you get for that length A?
9.57.
9.57. So that A value, 9.57. And that is larger than the 8.2, and that shouldn't be surprising. That is our hypotenuse. The hypotenuse should be the longest leg or longest side of a right triangle because it is opposite the largest angle. That length C1, this length down here, that length is opposite the 31, so it's opposite our smallest angle. So we would expect that to be the smallest side. That's why I was wondering, Madeline, what you meant by small, because this one is the smallest side of that triangle, but it's actually going to be the second largest side of this triangle. So that's why I was unsure what you meant. And again, that's going to come up a lot in chapter 7, the whole which side has to be the biggest, smallest, or medium side based on the angles and their comparative size. But that 9.57 should seem reasonable in scale. If we want to find this C1, just to finish off that triangle, if we're going to stick with the 59-degree angle, what trig function do you want to use? You've got lots of choices.
I would assume you can use any, right? Since you have the angles to all of the sides.
Since we have both angles, we could use really any of them. If we're going to stick with the 59 degrees, though, that limits our choices a little bit. Sort of. But there are good choices and there are better choices. So one of the things that, particularly for those of you going into physics, engineering, chemistry, that sort of thing, one of the things you want to get in the habit of is, when possible, trying to always use given information. So the information in this diagram that is in yellow is information that we were given by the problem. That 31, we calculated. The 9.57, we calculated. So it would be best, habit-wise, for us to use the 59 and the 8.2 in our calculations and avoid the other values if we can. Does that seem reasonable? Sometimes you have to use information you calculated to find other things. But if you don't have to, it's best to be in the habit of not. So if we're going to stick with that 59 degrees and use that 8.2, which trig function should we use?
I'd use cotangent,
But I don't like cotangent.
but it puts your variable in the numerator as opposed to the denominator.
But should we fear having variables in the denominator?
Yes, I do.
I do too.
Well, then we need to get past that by putting it in the denominator. Fair?
Cool.
Maybe that's not fair. I don't know. Better to be in the habit of not being resistant to that. And I actually have seen people who they will do anything to avoid that, and it just causes them pain later. Anyway, I specifically made these diagrams so that you'd have to deal with that over and over again. So using tangent because we know the opposite and want the adjacent means opposite 8.2 over adjacent, which is the C1. What do you not like about having the variable in the denominator?
It just feels like it adds 2 more steps to the process.
Well,
Yeah,
Just-
because then you have to go through the whole problem of like multiplying the denominator on both sides to cancel it out and move it to the other side. It's a lot.
no, you
Yeah,
don't.
not-
Just flip them.
Is that allowed in
Yeah.
math?
Well, we'd have to prove it. If A equals B over C, then AC equals B, thus, what am I going with? C equals BA. So if A equals B over C, then C equals B over A. Now it's a theorem. Now at the theorem, we proved it. Now you can do it every time you ever want to.
I need time to let that marinate in my brain.
Well, and that's one of the reasons I say don't be afraid of it, because once you kind of get used to doing it, it just becomes, oh, those are going to flip. Oops. Fair? Like, are we allowed to do it? Well, we're allowed to do it if we can prove that it's true, and it is always true. We proved it. So, yeah. But what are you going to do every time? You're going to multiply by that A, and then you're going to divide off that sign, right? So those are just going to flip. Now, Erin, can I use tangent?
No.
No, too bad. So what does that end up being? Approximately
4.93.
4.93. That seems reasonable. It was supposed to be smaller than the others, so being opposite the smaller angle, so that seems reasonable. Then what about this B? What trig function are we going to use?
Cosine?
Okay, if you want to use cosine, that would be cosine of what angle?
57.
Of the 57. So if you
Right, we
wanted
need to
do
use
that-
the provided ones, right?
Well, it's a good habit. You know, because technically we don't know if that 33 is exactly 33 or if it's 33.4, like how it should be around. We're like, best by habit to use given information. But if you wanted to use cosine because you like cosine, you could use the 57. But by habit, you're right. We should use the 33, which means we're going to be using sine since we have the opposite and want the hypotenuse. But oh no, the variable's in the denominator.
Yeah.
Oh no. We can just flip them. Always have to remember, don't mock students. Don't mock students. It's bad. Don't mock students.
I only feel a little bit mocked.
Okay.
I don't know about Aaron.
Mocking motivates me, so keep going.
So what's 8.2 divided by the sine of 33 degrees? 12 or something? 16, 15? I don't know. You guys have calculators.
15.055.
15.055?
Yep.
It's awfully specific, but that's okay. 15.055. Take a minute and find that C2 for yourself. And yes, Aaron, use tangent. You know what? You don't want to use tangent? Go ahead. Use cotangent. But the one divided by tangent that you're going to have to use to find cotangent is just as irritating, if not more.
All right.
I should do that. Since mocking helps you, I should really do that. Cotangent of 33 degrees is equal to adjacent over opposite. Don't write this down, by the way. I'm just doing this to hurt Aaron. So the cotangent
I'm writing it down.
33 degrees equals our adjacent is what, the C2, and the opposite is the 8.2. So that means 8.2 times the cotangent of 33 degrees is equal to C2. But that means 8.2 times 1 over the tangent of 33 degrees is equal to C2. So 8.2 times 1 over the tangent of 33 degrees equals C2. Yeah, that's so much nicer, right? But wait, if we used tangent and just flipped them, that would have, okay. And really, anytime you find yourself not doing something because you don't like it mathematically, that tells you you should be doing it, you know? Like, I don't like dealing with fractions. That means deal with fractions. I don't like radicals. Play more, go with radicals. I don't like math.
Sounds
Be a history
awful.
major. But it is the road to happiness. Anyway, what do we end up with?
12.63.
12.63. So 12.63. So the original question, find x, would just be that sum, but we added a whole bunch of other things that we could find. And really, frankly, if we took all of this, this is section 5.5. It's just a bunch of triangles. So there was a lot there. Questions about any of that?
I'm not quite sure why we used tangents to find the length of C2.
Well, C2 in reference to the 33, C2 is our adjacent side, right?
Mm-hmm.
And the 8.2, the given, is the opposite side. And which of our trig functions deal with adjacents and opposites? Well, the cotangent does and the tangent does. The tangent is one of our primaries, so we used tangent.
Could we not use cosine since we also know the adjacent of
Well,
the
hypotenuse.
hypotenuse? Yeah, sorry.
Yes, we could have. But as I was saying, it's good to be in the habit of trying to use given information when you can. But could we have used the cosine of 33 degrees is equal to C2 over the 15.055? Absolutely.
Okay.
And you can check. That
It's
should
just-
give you.
It's just a matter of taste.
Yeah. Also, no one has suggested, but if we, as soon as we know that 15 and the 8.2, what else could we use to find C2?
Sine.
I heard it really quietly in the background. Pythagorean theorem.
I did that the first time, and then you were telling us to use sine cosine, so I erased that and redid it.
Well, you had to have used sine to find the 15, right? Could we use the sine function like you said? Yes, we could use the sine function, but we'd have to have switched to the 57-degree angle. But if we wanted to, we absolutely could.
Okay, I'm confused on like why we have to use certain like functions with different angles. Like that's confusing.
Well, when we talk about this is one of those mean questions, not your question, my question. We know this is the hypotenuse, right? It is the hypotenuse because it is the long side. It is also the hypotenuse because it's the one opposite the right angle. Now, again, this is not a polite question on my part, but which side is this?
I suppose it depends on what angle you're using as your reference.
It does. This side is the opposite side if you're talking about that angle, because it is the side opposite that angle. And this would be the adjacent to that angle. But if we're talking about this angle up here, then this side length is the adjacent length, and that one's the opposite. So because opposite and adjacent is dependent on the angle of reference, if we change from one angle to the other, we change from opposite to adjacent. We essentially change from sine to cosine. That's actually what the co means in all of our co-functions, the cosine, the cosecant, and the cotangent. The tangent is equal to the cotangent of the other angle. It's its complement function. Now, why doesn't that happen when we talk about our circles? The reason it doesn't happen when we talk about our circles is because we are specifying in our circles that our angle is measured from standard position. So it is being measured from an x-axis. That makes our quote unquote opposite sides always are verticals. Fair? So we can say that's a y value. If it's in a triangle, there's no standard position in a triangle. So which side is our opposite depends on where we are looking. In our circular definitions, we are always looking at the angle in reference to the x-axis. Does that distinction make sense?
It makes more sense now.
Okay. And part of the reason that is a little bit weird is because it's not something that is universally cut and dry. It's a choice. For example, later on, when we start talking more about things like navigation, we will often be given angles measured from north, because that's how navigation people talk. Fair? And we will have a choice. Do we want to, let's say this is 40 degrees. Do we want to change it to a 50-degree angle measured from standard position, or do we want to stick with that 40? If we stick with the 40 and use the 40 in our calculations, then the horizontals become our opposites, become our sine values, and the verticals become our adjacents, because we've changed the angle of reference. Can we do that? Yes, as long as we are careful. Fair? So in some ways, when we talk about our circular definitions, it seems very strict because all our circular definitions have that phrase measured from standard position. As soon as you change that, you gotta define everything as the side measured orthogonal to the original side, and it's just so much worse. Fair? Okay. Okay. What else you guys got? Questions about all that? We still didn't convert this. Don't think I forgot. How do we convert 195 degrees into radians?
I times it by pi over 180.
Multiplied it by
Yeah,
pi over 180.
that's a bad habit of mine.
It's a bad habit of a lot of people, and I will do what I can to break you of it. Again, mostly through mockery. It's the only tools I was taught as a child. And it sounds so sad. So technically that's radians. That would be a little bit impolite for us to leave. We should reduce that fraction. What would that be?
I reduced it to 13 pi over 12.
13 pi over 12. Anybody want to back that up?
That looks right.
Cool. If you got a decimal approximation, I would ask why you're getting a decimal approximation. But it would have been
Well,
what,
I didn't give you a
3?
decimal
That's good.
approximation, so
But that would
you
be
can't
what,
ask me that.
3.4 or something like that. But yeah, exact values, great. That's what, back a ways, but that's okay. You guys doing okay so far?
I'm struggling a little bit with things like linear velocity and angular velocity, and knowing how they're different from each other.
Linear velocity, you got to be careful with the word linear velocity. That puts into our heads often, if it's a linear velocity, it should be going in a straight line. It's not what that means.
Well, that's just what I've read in the textbook, that
Yeah,
there's
but-
linear velocity and angular velocity.
Right, but linear
But somehow
velocity
they both
doesn't
deal with
mean,
circles.
yeah, well, because linear velocity does not mean straight line.
Oh,
Linear
gross.
velocity means speed with a linear measure. Linear measure means things like feet, miles, a length measure. So if you're traveling around a circle, if you're here and you're traveling along the circle, and we asked, you know, how fast are you going? Well, you'd be going so many, you know, feet per second, because you'd be traveling in feet. You know, you'd be going, you know, so many feet every second, right? That is a linear speed because it is a one-dimensional length per time, even though it's going through an arc. Fair?
Mm-hmm.
So that's a linear speed. By comparison, an angular speed is a rotational speed. So say you were going, you know, this thing was spinning at, say, 20 degrees per hour. Now, that doesn't tell us anything about how long it is, right? It doesn't tell us how long this is. It just tells us how many degrees that this thing goes every hour. So angular speed is a rotational speed, where linear speed is a distance moved. Fair? And how do those things relate? They relate that the linear speed is the radius of the circle that it's going around times the angular speed, as long as that angular speed is in radians. So this 20 degrees per hour would technically be kind of irritating. I'd want to change that into radians per hour really fast, because that allows us to use that nice, nice relationship. But yeah, you got to be careful about that linear. It doesn't mean straight line. It means length.
Okay, so linear velocity would just mean like how fast an object is moving around a circumference.
Yep.
And angular velocity is how many times a thing spins around in a circle.
Yes.
Okay. Do you think I don't know if you have any like questions in your bank of knowledge just off of those concepts, but if you have some, I would like to practice with you.
Well, since those are very commonly gotten completely and horribly wrong on the first test, that is not a bad idea at all.
Awesome. I love having good ideas.
So let's say we've got the proverbial Ferris wheel. Everybody likes a good Ferris wheel, right? And that Ferris wheel has a radius of 10 feet.
That is a tiny Ferris wheel.
How big is your Ferris wheel? That's right.
Dang, dude.
So 10 foot.
Touche.
Yeah, a little 10 foot Ferris wheel. It's for like puppies. I don't know. Little 10-foot Ferris wheel. That Ferris wheel is, well, if it's puppies, it should be going pretty slow. This wheel spins at, well, let's just say 2 RPM. Now, I am expecting you guys to know what RPM stands for. It is rotations
Rotations per minute?
per minute.
Okay.
Do try to avoid saying RPMs, You can, people often do, but it's not rotations per minutes, right? It's this many RPM, but people often say RPMs. No one's gonna think too badly of you, I hope. Anyway, this wheel spins at 2 RPM. How fast is the puppy going? Assuming the puppy is on the edge. Little ears getting thrown back. Looks more like a rabbit. Never said I could draw a puppy. So take a minute and figure out how fast that means the car is going. And one of the reasons, by the way, it's a linear speed. If it really bugs you, like it's linear, it should be a straight line. At any particular moment, this car is actually going that way. If it suddenly let go of the wheel, it would fly in a straight line that way at this linear speed. Fair? So if you really like, it should be going in a straight line. It's trying to, it's just being pulled back by the wheel. So if that helps, great. If it doesn't, and that made it worse, pretend I didn't say it. Now, I keep saying radians per time. Why do I keep saying per time?
Couldn't time be anything? It could be like, oh, radians per minute, radians per hour, radians per...
Yeah, radians per whatever's handy, whatever unit you want it to be in. So since we're given this information in minutes, we could certainly do it in radians per minute. It kind of depends on what unit we want for how fast this puppy is going, though. You want to know how fast the puppy is going in meters per second? We'd have to convert the 10 feet into meters, and I don't want to do that. Feet per second is a pretty standard measure of speed. Miles per hour, we could do that. How about we stick with feet per second? So you'll have to do a little bit of converting, but not as much as miles per hour. And feet per minute, nobody talks in feet per minute. Well, somebody probably does, but it's not standard. And Aaron, this gets back to your comment. If the only reason you don't want to turn it into seconds is because you're not good at dimensional analysis, you should be turning it into meters per year just to get to practice.
I thought the only answer to this was just Pythagorean theorem, right?
70% of the answers. Another 10% is dimensional analysis. The rest of it is trig. Dimensional analysis, though, it's one of the more powerful mathematical tools you can wander around with. It is so useful. mean, I don't know if I should tell you this, but when I was taking chemistry, I hated chemistry. Hated chemistry. I think I just didn't like my chemistry instructor, but I hated my chemistry class. So didn't pay attention, didn't do almost anything. So, but I could do a lot of the work, particularly on tests, because of dimensional analysis. They gave information in units and they asked for an answer in some units. Well, I can make those units into those units. The teacher would say, like, well, why did you choose to do it this way? Because the moles canceled. Well, yeah, but why didn't you do it this way? Because the moles cancel. I didn't know it. But you've ignored the charges. Moles, it can get you through a lot. But we do have to know our conversions. One rotation has 2 pi radians. We also have to get rid of our minutes and put in seconds. So knowing that there are 60 seconds in a minute is certainly handy. So how about 4 pi radians per 60 seconds, or an omega of pi over 15 radians per second. I kind of hesitate to say that V equals R omega is our fundamental relationship, because really it's just a version of that arc length equals radius times angle in radians. This V equals R omega is really just that pink relationship moving over time. So whichever one you want to think of as the fundamental is really up to you. But instead of length and angle, we have length per time and angle per time. It's the same relationship. So that linear velocity is literally just our 10 feet times our pi over 15 radians per second. Not quite sure why I'm writing everything's units on it. Probably just because we've done dimensional analysis, so I feel like I should. Those are going to reduce nicely. So how about 2 pi thirds feet per second? So a little more than 2 feet per second. So, you know.
Wait,
it's
how
good
did you simplify at the middle part where you turned 10 into 2 and 15 into 3?
Well, if you prefer getting the 10 pi over 15 first, you certainly could. But there's a 5 in that and a 5 in that. Divide both of those by 5.
Oh, okay. Okay. Thank you. I just
Sure.
didn't see it.
One of the things to be careful of about this type of problem is it's one of the only things in this course that we won't kind of continually use use and reinforce as the course goes along. Just about everything else, by the time we're in week like 8, you look back at the week 1 and 2 stuff and you're like, this is all obvious now. We use this all the time, day in, day out. I don't even have to think about this stuff anymore, except for this rotational stuff. Fair? So it is a good, I'm glad you asked this, because it is something that we have to purposefully reinforce. Fair? Particularly as you get prepared for that final. In 9 weeks. Don't worry about it now, but it is a good type of problem to make sure you're continually comfortable with. Okay. What is, let's say, the tangent of 13 degrees multiplied by the secant of 13 degrees exactly? Now, the term exactly, hopefully you've gotten used to this already in your mathematical careers, but the term exactly should translate to you into don't use a calculator. Calculators give you decimal approximations. They don't give you anything else. Now, this 13 degrees is not one of our standard angles. It's not even a nice cut of one of our standard angles. So finding an exact value just as a number, we're not going to be able to do. But we can simplify this. So what is it exactly? It's still going to be a trig function, but can we simplify it? I don't know why I've been big on the thought bubbles today. Can we simplify this? So can we use what we know about algebraic simplification to start manipulating these functions to make nicer statements? And to do that, or to handle this question, to help us do this, I want to look at some relationships based on our definitions. So if we look at just our unit circle definitions, the sine was supposed to be our y values and the cosine our x values, while the tangent function was supposed to be our y values over our x values, right? Well, if the tangent was supposed to be the y values over the x values, and the y values are supposed to be the sine function, and the x values are supposed to be the cosine function, that means that we can take, anytime we want, the tangent function and break it up into sine values divided by cosine values. Does that seem reasonable? Similarly, if we look at the cotangent function, cotangent function is supposed to be x over y. But again, if our x's are supposed to be cosines and our y's are supposed to be sines, we get the cotangent function. It's the cosine divided by the sine instead. Or heck, just knowing that the cotangent is supposed to be the reciprocal of tangent would have told us that, right?
So when talking about simplifying the tangent of 13 degrees times the secant of 13 degrees, are you suggesting that we turn the tangent of 13 degrees into a fraction,
Sure,
like a whole fraction number?
if you insist. Times the secant of 13 degrees. Now, is that a better statement? I don't know. But is it a manipulation we can perform? Absolutely.
Yes.
What about this secant? Well, we know secant is supposed to be the reciprocal of cosine. It's supposed to be 1 over the cosine function. Just like the cosecant. Oops. The cosecant is 1 over the sine. I don't know why I put parentheses there. They're fine to be there, but I don't know why I bothered. So where we see this secant, we could say the sine of 13 degrees over the cosine of 13 degrees. That was our tangent. Times 1 over the cosine of 13 degrees. So it's unfortunate that nothing cancels out in here, but we could certainly bring these together. The sine of 13 degrees over, well, the cosine multiplied by the cosine. If it was x times x, we'd say x squared, right? If it was a times a, we'd say a squared. So can we say the cosine of 13 degrees squared?
I thought that if numbers were on the denominator, when you multiply them, it just stays the same and you only pay attention to the
That's when you add.
complement. Oh, thank you, my bad.
No problem. This notation has some problems. For example, if I write, say, just the cosine of x squared, it's a little ambiguous. Am I saying find the cosine of the square of x? Even there, is that, am I supposed to be finding the cosine of the square of x? Or am I supposed to be finding the cosine of x and squaring that result? So written like this, it's a little bit unclear. With the parentheses there, it might imply a little stronger that I mean to square that. But trust me, you start doing things like, you know, the sine of 2x plus 3 squared. Wait, do you mean square this and then find the sine, or do you mean find the sine and then square it? And that ambiguity causes enough confusion that this notation, the way this is written here, is considered somewhat invalid because it's so confusing, because it's so ambiguous.
Could you not just use like multiple parentheses?
We could, if we wanted to say the square of the cosine result, we would have to, if that's what we wanted, put an extra set of parentheses around that like that. But I don't want to write an extra set of parentheses like that every time because I'm super lazy.
Is it root sine over cosine to get rid of the square in the bottom but still make the relationship equal?
Say that again?
Root sine over cosine?
No.
No?
For a couple reasons. Well, one, you can't take the square root of a fraction and have it maintain value.
That makes sense. Yeah.
because that would make 1/4 the same as 1/2. Because the square root of 1 is 1, square root of 4 is 2. To avoid that ambiguity, when we're squaring a trig function like this, we do something that might seem a little strange. We put the square on the function. So we read that as cosine squared 13 degrees. That tells us unambiguously, find the cosine of 13 degrees and then square that result. If the square is anywhere else, if we left it behind there, then you'd be squaring the 13 and having to deal with it with whatever a square degree is. Don't do that. So that's going to look a little bit weird for a short time, but then after a while, it seems more reasonable. So, is this statement better? Is it simpler than this one? Well, not necessarily, but it is written in functions that we like more. We'll tend to like sine and cosine better than secant, especially. Fair? And it is especially fun when you have things like the cotangent of theta multiplied by the sine of theta. And you're like, oh, I got two functions multiplied together. I've got cotangent and I don't like cotangent. Oh, this is just going to be irritating. But what is cotangent supposed to be equal to?
Cosine over sine.
It's supposed to be equal to the cosine of theta over the sine of theta times the sine of theta over 1 if we want. What's going to happen to those sines of theta?
They're gonna cancel out.
Absolutely. Making this just equal to the cosine of theta. That's nice, right? So one of the things we're going to play with some at the end of this section, this is technically in 5.4, is trying to get in the habit of using some of these kind of algebraic simplification ideas mixed with the identities that we get. These are called our identities. These are our quotient identities. These two and the cotangent equaling 1 over the tangent are our reciprocal identities. So using these identities to be able to manipulate statements and simplify them down into handier statements. And we'll play with that some. And we're actually going to build up a whole list of identities, a whole list of equalities and tools, things that we can use to replace one statement with another to be able to simplify our work. But we'll build most of those in chapter 6.
So how would these types of math problems be applied in like the real world, like story problem wise? Or is it mostly just a thing to exercise your brain?
Right now, it's more of a set of learning a set of mechanics, a set of manipulations. How these come up in story problems is a little bit beyond some of the things that we're going to do right now. But when you get into things like physics and calculus and you're looking at, what is the hydrostatic pressure on the end of this trough, and you're taking, using this angle to figure out the height and width of that trough and taking that height and multiplying by the depth to get the pressure. And you end up taking things like, 8 times the secant of that angle multiplied by 4.3 times the cosine of that angle, because you're finding those different lengths and those different heights, recognizing that, hey, secant times cosine, that's cosine times 1 over cosine. Those things cancel out. So they occur in fairly, in story problem wise, they will occur in fairly dramatic scenarios that are going to be a little bit outside of what we're doing right now. But
Yeah, that looks real hard. I don't want to do that.
But what you're kind of preparing to work toward. Fair? So right now we're just looking at the mechanics, almost making them into kind of what will hopefully be neat little puzzles, so that later we can go, so that later you'll have those manipulations. That type of problem, by the way, is Calc 2. For those of you going into calculus, as soon as you hit, usually it's about Calculus 2, most Calculus 2 students go, oh my gosh, I wish I paid more attention in trig identities, because those relationships make those problems so much, drive so much of how those problems work. Fair? So for us, story problems with these, not so much. They'll just be mechanics. Later, there will be some very cool story problems with them, but you need some other tools along the way. See, there is one more major identity I want us to look at. And before we trundle off today, I said these were our unit circle definition. So based on our circle, if we know the X and Y coordinates of the point of intersection with a ray at a particular angle on a circle of radius 1, that was our cosine was the X value, our sine was the Y value, and so on. The equation of that circle is supposed to be X squared plus Y squared equals 1. That's our Pythagorean theorem holding. For every point on that circle, the square of the X plus the square of the Y should equal the square of 1, because our Pythagorean theorem holds. But again, if our X value is supposed to represent the cosine, then the cosine squared of our angle plus the Y value is supposed to be our sine function, the sine squared of our angle should always equal 1. So let's say, for just real quick, for sake of argument, say you know the sine of theta is equal to 0.7. And somebody said, okay, find the cosine of theta. Well, there are a couple ways to do that, but one of them, knowing that the sine is 0.7, we know the cosine squared of theta plus the sine 0.7 squared should equal 1. So 0.7 squared equals 1 minus the cosine squared of theta. Why did I do it that way? That was crazy. Sorry. The cosine squared of theta equals 1 minus the 0.7 squared. So 1 minus 0.49 or 0.51. So what's the cosine squared of theta? Well, the cosine squared of theta is 0.51. So what's the cosine of theta?
Just square root of 0.51.
Plus or minus the square root of 0.51. Do we know whether it would be positive or negative? Since we don't know what quadrant we're in, we don't know whether it's positive or negative. Fair? One of the ways we'll see this come up, let's say we have 1 minus sine squared theta divided by cosine. I don't want the square there. Cosine theta. Because again, that's, some big angle problem that we're dealing with a setting thing and a trough with pressure and electricity and, whatever we're doing, this ratio comes up in our problem. Again, for right now, we'll just be doing it as a mechanic. But if you had to use some big tools on this expression, that could be kind of annoying. But if the cosine squared plus the sine squared is supposed to be equal to 1, if that's always true, that means, that means that cosine squared is always equal to 1 minus sine squared theta. If we just subtract that sine squared off. That also means we can always replace sine squared with 1 minus cosine squared if we wanted to. So here, this 1 minus sine squared, what's 1 minus sine squared equal to? It's equal to cosine squared. Well, what does that mean we can do with these cosines? That one's going to cancel with one of those, leaving us with just cosine theta. Again, these are just manipulation tools. Things that we can do based on the definition of our trigonometric functions. Yeah, the spacebar unmute thing works sometimes for some people and doesn't work other times for other people. I'm never sure why. So
I think it's when I had the chat open, it was messing with it because it thought that I was putting space into chat as opposed to holding spacebar to talk.
Yeah, maybe. And sometimes people will just turn their sound on and leave it on. And I often eventually mute them because there's usually some feedback or static or something. So often I'll go in and manually mute you. Not you necessarily, Nick, but people with either background noise or static. So not to overwhelm you too much, but this Pythagorean identity, this is a big deal, by the way. This identity will come up a lot. Remember I said Pythagorean theorem is the answer to like 70% of the questions. One of the reasons is because this identity is so powerful. And it's our Pythagorean identity. So not only can we take this primary Pythagorean identity and express it in a couple of different forms. Again, this is the same identity, just solved for either sine squared or cosine squared, depending on your needs. But also we could take this whole statement and divide it by, say, divide both sides by cosine squared. Why would we want to do that? It doesn't matter why. Let's look at what it would do. Cosine divided by cosine would be 1. What is sine divided by cosine? I know you tried to say tangent. I saw you, but Mike didn't work.
Is it tangent? I was thinking that, but then I was like, that doesn't sound right.
Yep. Sine over cosine is tangent. So if it's 2 sines and 2 cosines, that means it's 2 tangents. So it's tangent squared is equal to 1 over cosine squared. Well, cosine, 1 over cosine is what?
Secant.
Secant. So it's 1 over cosine times 1 over cosine. So it's secant times secant. So it's secant squared. So that gives us another Pythagorean relationship. And we could equivalently use it as tangent squared theta equals secant squared theta minus 1. We could use it in that form if you wanted to. Or secant minus, or secant squared minus tangent squared is equal to 1. You can manipulate it all you want. Well, that's just by dividing by cosine. You think we could instead divide by sine squared? And get another relationship? I'm assuming your answer is a resounding yes. Cosine divided by sine? Cotangent. There's 2 of them, so squared. Sine divided by sine? 1. 1 divided by sine is cosecant, and there's 2 of them, so cosecant squared. So these as a group form our Pythagorean identities. You will use this primary one and its forms most of the time. Mostly when you use your Pythagorean identities, it'll be that primary one. But tangent and secant are both really important and really powerful functions. They come up in a lot of applications. So sometimes you'll be using that tangent squared and secant squared. Particularly secant, tangent's a little hard to work with in some bigger applications. Secant can be actually really hard to work with in certain applications. And this Pythagorean identity gets you out of that trouble a fair amount. I can't think of a single instance where I've ever used that one for anything other than a problem that was just asking you to do it. Like an actual practical application problem where the cotangent, cosecant Pythagorean identity was useful. Hence my tendency to disregard cotangent, Aaron. It's just, it rarely comes up as a useful tool, you know. But it does every once in a while. It is a nice relationship to know, but not often. But yeah, you guys will be fairly surprised, even in the applications that we will look at, how often that Pythagorean identity will just pop up. But try to remember that Pythagorean identity is just saying you're on a circle. So anytime the fact that there's a circle involved is handy, this statement really just says, by the way, cool things happen because we're a circle. Fair? All right. So we're going to play a little bit on Wednesday as we review with some kind of small ways to use these identities just to simplify statements and prove other statements. In chapter 6, we'll build some more complicated relationships. If you're worried at this point about, gosh, have I supposed to do it? If you're worried about even saying it, my goodness. If you're worried about, do I have to memorize all of these relationships? The short answer is no. You will have a sheet that you're allowed to use during your tests that has all of these identities and more on it. All the identities we'll do in the next sections as well. But many of these you kind of already know. The reciprocal identities, hopefully you've been thinking of secant and cosecant in terms of the reciprocal of sine and cosine. The tangent and cotangent, tangent being sine over cosine. Most people get to that fairly comfortably, and it becomes something that you know. This Pythagorean identity we will use so often, you'll get super comfortable with it. These secondary Pythagorean identities, oftentimes people will go, I think it's this, let me look it up. That's why you've got your sheet, you know, so you can look it up if you're not sure. Some of the bigger half angle formulas and double angle formulas and angle sum and difference formulas that we'll build in chapter 6, that starts to be a lot just to kind of memorize and be carrying around with you. And I don't want you guys to be spending your time memorizing stuff. I want you guys to be learning stuff and learning how to build stuff. So you will have a sheet that has all of these on them. There are some of them that it will be beneficial for you to memorize as you go on in your courses, just because they come up so often, and I will point those out to you as we go along. The big one of those is this Pythagorean identity. This is something that should become super, super natural as fast as you can. Sine squared plus cosine squared is 1. That is one of those fundamental truths that just comes up a lot. Cool.
So I have a question about the Pythagorean identity.
Shoot.
So with the circle, and you know how there's, you know, the coordinates, is one the coordinate that's equal to 2 pi?
Is 1 the coordinate that's equal to 2
So,
pi?
like,
I'm not sure the question.
Yeah, so like on the horizontal axis of the circle, on the far left would be like 180 degrees. I'm wondering if that 1 in the Pythagorean identity is the coordinate in 1 and 0. Does that make sense?
It does, but I think that's just a specific case. So the 1, or sorry, it's the 0, 1 that's there, or the 1, 0 that's there. If you put either of those into the Pythagorean identity, sure, you get the 0 squared plus 1 squared is equal to 1. True. This 1 does make that 1 have to happen. But also, if you take any of them, if you take that square root of 3 over 2 1/2 point, well, take the cosine, the square root of 3 over 2 squared plus 1/2 squared, and try to figure out what that's equal to. Well, that's 3/4 plus 1/4 equals 4/4. That's 1. It's always 1. It has to be 1. So this 1 isn't because of this, it's because of all of them. Fair? These, they're called the coaxial points. These coaxial points just make that 1 blatant because the other part is 0. Fair? But this,
Okay.
does that make sense how I'm trying to express that?
Yeah, a little bit.
So it's not specific to that 1 at 0 and 2 pi, just like it's not specific to the 1 up at pi over 2 or the -1 at pi. It's that they all add up to that 1, just the coaxial points, because of the 0, that 1 is all that's left.
So is it safe to say that the 1 could be considered a rotation?
Which one?
the one in your theorem over here.
Oh, this one?
Yeah.
The best thing to associate that one with is the radius.
Yes. Okay.
Because
Okay. got
that's
it.
really what's causing that one.
Okay.
Cool.
So that one would be applied to like the unit circle?
Yes.
Okay, so if the circle was, I don't know, a weird radius, that one would then be that radius,
It would be the square of that radius
the square of that radius.
because
Okay,
it's Pythagorean theorem. Because remember, this comes from, where is it? Our circle definition down here. This is where that Pythagorean identity came from, right? That one is there because we're a circle of radius 1. If it wasn't a circle of radius 1, it would be x squared plus y squared equals r squared, right? But we couldn't replace this x and this y with cosine and sine anymore, because off the unit circle, cosine is equal to x over r, right? So if we wanted to replace that x, we'd have to multiply the r over and say that that x is r cosine theta squared plus r sine theta squared equals the r squared. But couldn't we then just divide off all those r squareds and end up right back here? And the short answer is yes, we could. So that's just, that one is that scaling radius, but because those ratios are the same no matter where you are on that scale, it's always going to ratio down to cosine squared plus sine squared equals 1. Whether we're on the unit circle or not, that always has to be true. Does that help? Okay. But yeah, I think the best thing to associate this one with is that radius. If you're looking for it to have, if you're looking for a physical meaning for it. So a lot of stuff here to play with. Again, you guys should be diving into really all of chapter 5. On Wednesday, I want to have a nice review. I think my open math says your test is Friday. Does I recall? Is that not true? Am I making that up?
I'm looking right now.
It says that there's some homework due on Friday, 29th.
Right there. Information about test 1, chapter 5 on that weekend. And the homework's due then. But we'll talk on Wednesday. I let me know if you guys are like, could we have another day or two? But really, as I said, we've gone through all of these tools. I mean, 5.5 is the right angle stuff. So we'll talk more about it on Wednesday. But that test being end of this week-ish, I think is best for us as we go along. Cool.
Is that going to be open just that one day, Friday, or is it open for the weekend?
I tend to prefer having them open one day just because so just because it feels more secure, you know. But we can talk about that if that's going to be an issue. Fair.
Is it gonna be open until midnight on Friday, or is it gonna be
Yes.
open until like a specific time?
Both. It will be
Okay,
open to a specific
midnight
time,
is the specific
and that
time.
specific time will be midnight.
Okay.
Okay. Anything else, you guys? Okay. I didn't get any requests this weekend for videos or anything. So if something comes up, do remember you can ask me to make you something or send you something. And I'm happy to do that and post that. I noticed you guys haven't gotten, most of you looking at the grade book haven't gotten much past 5.3. So maybe as you go into 5.4 and 5.5, you'll have more stuff that you want to ask. So if that comes up between now and Wednesday, let me know. Or if you just want to send me often a nice messages, hey, can we look at this problem during class? Those are great. Then I can have a bank of questions that we can look at as we start, and we can bang those out real quick. So let me know what you guys need. All right, then that's our time. I guess I'll talk to you guys on Wednesday if I don't hear from you first.
Thank you.
Have a wonderful day.
Thank you.
I had a quick question.
Yes, ma'am.
How important is it that I'm here on Wednesday? It's my birthday and we were gonna have a family dinner, and we didn't want to have it like super early because of class or super late
Right.
because of class. So
How important is it to me or to you?
in general, like, is there gonna be like something that I wouldn't be able to get just from reviewing on my own? Like,
No.
okay. Just want to make sure we weren't like covering any new topics. There wasn't gonna be like a test or something, because
Yeah, no. And really no new topics.
okay.
I mean, I'll try to say something meaningful and important, but
I mean, it's always meaningful, but like,
Right.
I don't know.
and if you want, you can send me a message on Wednesday and I'll try to remember to record our meeting, and then you can watch it later if you want.
Okay, that would be very helpful.
Okay.
All right,
Oh.
thank you.
Sure.
Bye.
I have a question.
Yes, ma'am.
So I emailed you last week about last week's lecture, and because I saw that you were recording, and I was wondering if I can have it sent that video if possible.
Yes, I thought I responded to that.
I think I sent it to you last week, so I don't know. I kind of forgot about it too. So
What I'll do, I usually like to record them, but what happens is as class starts, I often, get distracted by questions and don't start that. It's really helpful if somebody can go just like, oh, can you remember to record? And then I'm happy to.
mhm.
And where I put them will be, there'll be a spot that just says videos. This isn't your guys because I don't have one for you guys yet. But where I'll put them is on my open math. So there'll be a little block here that says videos, and I'll stick them there.
Okay.
Sure.
And for
And
this week, all we have to worry about is the homework that's due this Friday and then the exam, right? Correct?
Yes.
Okay. Just clarifying. Thank you.
No problem.
Thank you. Have a good day.
You too.